All right. Hello, everybody. So today we're going to talk, or in this video rather, we're going to talk about doubly linked lists here. I guess it might be a different day for you. I don't know. So in a singly linked list, right, each node has a next pointer that points to the following node. So you can start at the head or you can start at any node, but you can only go forward through the list and not backward. And there's some places where that kind of like affects the runtime of our operation. So like a big one is pop back. If you want to erase the tail in a singly linked list, you need to modify the next of the node right before the tail. But there's no easy way to get that other than by starting at the beginning and going forward all the way until you get to the sort of second to last node there. So out of the sort of like, four convenience functions, push back, push front, pop front, three of them run in constant time except for pop back, which requires a loop. And it's kind of like a weird sort of odd one out there like that. So in a doubly linked list, each node has two pointers. There's a next pointer that moves you to the following node, and then a previous pointer to move you to the prior node. So our node structure looks like this. Right? We have our value, which, for simplicity's sake, we're making those ints, but that could be whatever your list is a list of, right? Strings or floats or whatever. You could make a fancy template class, and then it would be the template type. And then we have two pointers here. We have a next pointer and a previous pointer here. So if we have a pair of nodes, A and B, then A's next takes me to B, but I can also choose to go backwards. B's previous takes me to A there. The head has its previous set to null pointer, and then the next of the tail is set to null pointer. So there's nothing before the head, and there's nothing after the tail there like that. So doubly linked lists have like an invariant. An invariant is something that should always be true, right? That sort of describes the relationships between adjacent pairs of nodes. So if you have a pair of nodes that are right next to each other, say A and B in the list here, then these two things down here, these two statements, these should always be true. This isn't like actually something that will like show up in your code, right? You'll never write like if A arrow next arrow previous equals A, because it should always be true. Like there should never be a case where this is not true here. So what this basically says is if you take one step forward and then one step back, you get right back to where you started. So if you're at A and you follow A's next, so if I'm at A and this is A's next right here, right? At A, I follow A's next, I get to B. And then if from that spot, I take the previous, take B's previous right here, okay? Well, I should get back right to where I started. I should get right back to A there. Same thing is true if you start at B, right? So if I start at B and I follow my previous, so if I'm at B and I follow my previous, that takes me over to A. And then from there, I follow that thing's next, takes me back over here. I should end up exactly back where I started. So whether you go forwards then backwards or backwards then forwards, you always end up where you started. And that should be true for every adjacent pair of nodes in a doubly linked list. The only places where this is not true are at the head and the tail, right? At the head, you can't go backwards because there's nothing before it. So it doesn't sort of like you can't go backwards and then forwards from the head. And likewise at the tail, there's nothing after the tail. So you can't go forwards and then backwards at the sort of tail there. But everywhere else, this should be something that sort of is always true. This tells you, is your doubly linked list kind of like in good shape? If it's not true, that means something is broken and things have gone off sort of weird here. So like the doubly linked lists are the contents of assignment 2. So the assignment 2 test script will test for these sort of two things basically every time you modify the list. It'll make sure that this is always true there. So we have some code that we built up from the singly linked list implementation, and anything that just goes forward, anything that just follows the next pointers, you can just reuse that code unchanged, like because nothing about the next pointers is changed by adding the additional previous pointer. So we can reuse a bunch of the sort of code that is just like starting at the head and going forward from the singly linked list here without needing to change anything. Anything that changes the list structure, like insert and erase and all of their sort of like friends there like that, those will all need to be modified because now we have this additional previous pointer that needs to be updated there. So we can't just sort of take the code for insert and use it directly in a doubly linked list. It's not aware of the fact that we have this like secondary pointer going on in here. So insertion on a doubly linked list, right? We need a pointer to something near the spot where we're going to insert. So remember, for like in the singly linked case, we have a node A. Try to sort of insert this here in the middle of the slide, right? And then A's next is going to point to a B. B is there like that. And then B's previous points back to A. And we want to insert something in between those two things there. So just like for the singly linked insertion, we're going to take a pointer to A, the node before the spot where we want to do the insert. For a singly linked list, we didn't have a choice. We had to pass A as the pointer into the insert function there because it is A's next that we need to update. But for the doubly linked list, we actually could choose to do it either way. We could have chosen to make the insert function take a pointer to B, because from B, we can go backwards. We can just go like B's previous and then get to A there like that. So for consistency with the singly linked one here, we're going to make this one work the same way. It's going to take a pointer to A pointer to the node before the spot. But if you're writing your own doubly linked list class, you can choose either way. You can either take a pointer to the node before or a pointer to the node after there like that. Just like for the singly linked list insertion, we have 4 cases that this is going to break down into. So like we could have, like in the picture that I drew up here, we have both an A and a B. Maybe we don't have an A, that's case 1. Maybe we don't have a B, maybe that's case 2. And maybe we don't have either. Maybe there's nothing before or after. That's case number 3 there like that. Unlike the singly linked one here, these cases are going to be a lot more symmetric here because our nodes themselves are symmetric. You can go forwards and backwards. So you'll sort of notice that in the cases, there isn't like a weird extra step that we have to add sometimes. It's just the steps change in the different cases here. Okay, so case 0, what if we have both an A and a B? And again, we're wanting to insert a new thing in between them, and we have A. B is, of course, just A's next there like that. So just like with the singly linked insert here, our step number 1 in all of these cases is always going to be create the new node here. So the new node's floating out there in memory wherever the allocator sort of found space for it there. The next 2 steps are going to be all about setting up ends pointers here. So where should ends next point to? It should point to B, and B is again really just A's next here. So our next step is going to be to set ends next to point to B, and we get B as A's next there. Now notice that like at this point the rest of the list has no idea that N exists here. Like if you're looping through the list here from the head, you don't see N at all there like that. So we're obviously we're not done yet here. Our next step number 3, is to set N's previous. So N's previous is here, right? So N now knows that A comes before it and that B comes after it there like that. So now N is aware of its sort of like, position in the list, but its 2 neighbors, A and B, are not aware that they have a new node between them. So the next 2 steps, steps 4 and 5, are going to be about updating B and A. So step number 4 is to update B's previous, this thing right there, and make that point to N there like that. So we're going to set B, and again, B is really just A's next. That right there, right? Set A's next's previous, or you could also get to B from N, right? From N, we could take N's next and get to B there if we wanted to sort of get there like that. We have 2 different ways to get to B at this point, but we need B to know that there is a new node before it. So if I was now like starting at the tail and looping through the list in the reverse direction, I will see N as coming between A and B here. I'll go B and then N and then A there. And then the final step is to update A. So we're going to set A's next to point to N. So at this point, if I'm going through the list in the forward direction, like that, I see the order as A, N, and B. And if I'm going through the list in the reverse direction, starting at the tail and going backwards, I see the order as B, N, and A. So the order is sort of consistent in both directions there like that. And at this point, I'm done. Now, as I mentioned in the singly linked sort of video, the order of some of these steps, not all of them, but some of them is important here. In particular, the last two steps here, you want to be careful about here. So let me back up a couple steps here to before we had done steps 4 and 5 here. So let's back up back to here. Let me just clean this up a little bit like this, right? What if we get the order of those last two steps wrong? So let's say that we did it in the step 5. So step 5 is where we updated A's next. Right. And then we did step number 4, which is where we updated B's previous. Right. So step number 5, we're going to update A's next here. So that means we're going to break this link here. Right, A's next no longer takes me to B. Now it takes me to N, right? So far so good. If you're looping through the list in the forward direction, like that, you see things in the order of A, and then N, and then B, right? But then my next step is to update B's previous. But the problem is, how was I getting to B? I was getting to B as A's next. But that's not what B is anymore. If I go to A's next, I get to N. So if I just blindly sort of do what the sort of step said, and I said, okay, I'm going to set B, which is A's next's previous, to point to N, what I'm going to do is I'm going to break this link right here and make that point back to N itself, like that. So now we have this like weird sort of setup here. If I'm going backwards from B, right? If I start at the tail and I loop through the list in this direction here, so from B, I don't see N, I just see B and then A. So B is kind of not aware that there's something before it. And then if I go from A into N, and then I try to go backwards, like I should get back to A, but I don't. I just get sort of stuck in this little cycle sort of going around there like that. Now, you could fix this. Instead of getting to B as A's next, you could get to B as N's next, right? Because N's next still points up there to B there like that. But then you'd have to sort of like change things around. It wouldn't be sort of consistent there. So like, you know, either pay attention to the order or at least pay attention to what does, you know, A's next, N's next point to at this point in the code, because those things are changing as we sort of go through stuff there like that. Okay, then we're sort of like that, right? Like once we're done, it should be the case that if you go from A to N and then backwards like that, you get back to A. If you go from B previous to N and then forward, you get back to B. And of course, if you do that from N, the same thing is true, right? If you go from N forward back, you get back to N. If you go from N previous and then forward, you get back to N there. So it's sort of consistent in both directions there like that. Case number 1 is, okay, what if A doesn't exist? That means A is a null pointer. So the parameter to the function, right? A is our parameter that the function takes, is a null pointer here. That means we're going to insert before the head. We are doing a push front operation here, inserting a new head. So the new node that we're going to create when we're done should be the head of the list here. So the first step, again, is always the same. It's create our new node. So our new node sort of appears out there like that. And just like before, steps 2 and 3 are all about setting up N's next and N's previous. So if you want, you might like pause the video here and sort of figure out like, okay, what should N's next be? What should N's previous be? And then resume it and see if you sort of got it right here. But those are, you know, pretty easy, I think. Where should ends next go? Ends next should point to B. So we set up ends next and point to B. Now we don't get B as A's next because A is a null pointer, right? We get B now as the head. That's how we sort of get to B in this situation here. What should ends previous be? Ends previous should be a null pointer, but you could get that null pointer from A. In other words, you could do, ends previous equals A, and that would give you the null pointer you need here. You can think of it as like grabbing this null pointer that is A and just copying it into there like that. The reason why you would want to do that is that would keep the code for step number 3 the same as in case 0. So you wouldn't have to change the code for that step 3 from case 0 to case 1 if you sort of notice that, hey, A will give me a null pointer as well there. And then steps 4 and 5, like before, are about informing the rest of the list about ends existence here. So before, step number 4 was about informing B, and it still is. It's setting B, and again, B, we get to B from the head. We're going to set B's previous to point to N. So now B is aware that there is a new node before it. And then again, like the previous one was about setting A's next to point to N, but A doesn't exist. A doesn't have a next here. So what are we going to do in place of that in step number 5? We're going to update the head. We're going to set the head to point to N. So again, like if you start at the head and you go through the list in the forward direction, you see N, and then you see B, and then you see the rest of the list there. If you're starting at the tail and coming in the reverse direction, you see B, and then you see N. And then that null pointer in ends previous lets you know that, like, if you're going in the reverse direction, you are done there like that. So my list is consistent in the forward and backwards direction. Case number 2, just like for the singly linked, if B does not exist, that means A is the tail. So that means A's next is a null pointer. In other words, we're doing a push back. We're adding a new tail. So when we're done, N should be the tail of the list here. So just like before, step number 1 is create the new node like that. So you could, factor that out and do that at the beginning of your insert function instead of repeating that step inside of each one of the other 4 separate cases there like that. Then we're going to set ends next. What do we set ends next to? We're going to set it to a null pointer. I could get that null pointer from A's next. Like A's next is a null pointer here. And again, like why would I want to sort of do that? I would want to do that so that I can reuse the same code as in case 0 for this right there, right? That would let me reuse that code instead of having to make all 4 cases like completely sort of different there. Step number 3 is going to be about ends previous. Where should ends previous point to? It should point to A. So now N is correctly set up, and again, step 4 and 5 are all about updating the rest of the list here. So previously, step 4 was about updating B's previous, but B doesn't exist. There is no B. So what are we going to do in place of that in step number 4? We're going to update the tail to point to N. So the tail, TL, kind of takes the place of B's previous that we need to update there like that. And then the final step, this step here, again, this is the same as in case 0. So this step doesn't change, only step 4 needs to change here. Like all of the other steps here could be the same as in sort of case 0 there like that. So if you're looping through your list in the forward direction, you're starting at the head and looping through, right? You will see A, then you will see N, and then you'll hit a null pointer that lets you know that you're done. If you're starting at the tail, you will start at N, you'll see A, and then you'll see the rest of the list. So you'll see N, and then A, and then everything after that there. So my list is sort of consistent in both the forward and the backwards directions like that. And then case 3 is kind of like the intersection of case 1 and 2. A and B don't exist, that means the list is empty and we're adding the very first node. Now, of course, if the list is empty, that first node is going to become both the head and the tail. So that means what we're doing here is both a push front and a push back. So this is going to be a combination of cases 1 and 2 here. Again, first thing we do, create a new node like that. Now, step number 2 is to set up ends next to null pointer. Now, I could get that null pointer from the head, right? I could do ends next equals head. And again, why would I do that? I would do that because that makes the code for this the same as in case number 1, like that right there. I'm going to set ends previous to null pointer, and I could get that null pointer from A. Now, again, why would I do that? I would do that because now that makes this the same as in case 2. There. So I could imagine sort of taking the A that we have here and putting that in there for like that previous there like that. And then steps 4 and 5 are all about updating the pointers of the stuff around N, but there are no nodes around N here. So in place of updating B's previous, I'm going to update the tail, set the tail to point to N. And again, where have we seen this before? We just saw this in case 2. And then in place of updating A's next, we're going to update the head. And where did we see that? We saw that in case 1. So the steps for this are just a combination of the steps that we saw previously here. 1, like that, right? You can kind of just combine the steps from this. So now if you start at the head, you get N. If you start at the tail, you get N, and our list has 1 node there like that. Okay, on to erase here. So in the singly linked erase, we had to take a pointer to A, the node before the node that we were going to erase. And that's kind of awkward. It's a little bit weird to sort of do that here. Here, though, our erase function can take a pointer to the node that we want to erase, because we can always take ends previous to get to the node before it, and we can always take ends next to get to the node after it. So the two nodes that need to like be informed of the erase are A and B, but we can get to both of them from N here. So the erase on a doubly linked list is much more natural. You just give it the pointer to the node that you want to erase. And just like for the singly linked, we're going to have 4 cases. But because we have next and previous pointers, these cases are going to be a lot more sort of symmetric and kind of like nice to work with here. You'll sort of see how they have like a nice symmetry to them here. So case 0 is the sort of general case. There's something both before and after N. So N is somewhere in the middle of the list here. So we're going to set B, and B is really ends next. Right? We're going to set B's previous to point to A, and A is really ends previous. Right there. Then we're going to set A, which again, A is ends previous. A's next to point to B, where B is really ends next, like that right there. And at this point, N is disconnected from the list, right? If I'm looping through the list in the forward direction, I see A, and then I see B. I do not see N. If I'm looping through the list in the backwards direction, I see B, and then I see A. I don't see N in the middle there like that. So once the rest of the list has kind of like, detoured around N, we're safe to do step number 3, which is to delete N there like that. One thing to notice in this case, so for this erase here, it is perfectly fine to swap the order of the first 2 steps here. Like whether you update B's previous first or A's next first doesn't matter, because N is sort of like giving us access to both of those things here. We're not using A to get to B or B to get to A here. So you can be a little bit more sort of loosey-goosey with the order of the steps here. Of course, deleting of N, that has to happen at the very end here. If I'm using N to get to A and B, I don't want to delete N and then try to use it to get to one of those 2 things around it. That's not going to fly. Case number 1, what if A is null pointer? So that means n's previous, right? N's previous right there is a null pointer. Well, the only node in our list that should have a null pointer previous is the head. So that means n is the head. We are erasing the head. That means this is really a pop front operation that we are doing here. So just like before, we're going to set B's previous to null pointer here, but we could get that from A, right? A is, again, n's previous. So you can imagine sort of taking the null pointer and copying it into there, or taking that null pointer and copying it into B's previous there. And the reason why you would want to do that rather than just doing like, B's previous equals null pointer is that makes the code for this the same as in case 0. So you don't have to write like a separate code for this step here like that. As if you can just use the exact same code that you use for step 1 in case 0, and it will also work here. Step number 2 was about updating A, but there is no such thing as A. So in place of that, we're going to update the head. The head is going to point to B, and B is going to be n's next here. So at this point, again, like, now n has been sort of pruned off from the list. If you start at the list at the head and go forward, you see B as the sort of first node you encounter. If you start at the tail and you go backwards, you get to B, and then B's null pointer previous tells you, hey, stop, you're done. Like, that's all there is sort of in here like that. So at this point, it's safe to delete n out of the list there like that, and then n is gone there. Case number 2 is the opposite of that. So if B doesn't exist, that means B's next, or excuse me, n's next. Right? That's how we get to B is as n's next. That means n is the tail. That means we are doing a pop back operation here. We're deleting the tail here like this. So step number 1, again, like previously, step number 1 is about updating B's previous, but there is no B here. So in place of that, we're going to update the tail there like that. So we sort of update the tail to point to A, because when we're done, A is going to be the new last node of the list here. Step number 2, if A is the tail, then A's next here should be a null pointer. But I could get that null pointer from B. I could get that from n's next there like that. And again, like, why would you want to use n's next as, like, instead of just saying equals null pointer? Because if you do that, that makes this the same as in case 0. So you could sort of reuse that code from case 0 there for that step there. Once you've done both of those things, the list is no longer aware that n exists. The only pointer we have at this point that points to n is n itself there. So then we can delete n and sort of, not leak memory there. Sorry, this should be case number 3. Messed up the number up there like that. So neither A nor B exist, right? So that means n is the last node. The only way we can have a node that doesn't have anything before it or after it is if we have a list with exactly one node, which means n is both the head and the tail. We're deleting the last node out of the list, so when we're done, the list should look empty. Head and tail should both be null pointer. And this is just going to be the intersection of cases 1 and 2. So we're going to set the tail to null pointer. Now, where did we sort of do that previously? We did that in case 2. So the code for this can be exactly the same as case 2. Then we're going to set the head to null pointer, which we could get from n's next here. So this one could be code from case 2. And then this one could be the code from case 1. They're just reusing the exact same code there. And then, of course, once head and tail have both been set to null pointer, we're free to delete n there like that. When head and tail are both null pointer, that means that my list is empty, which is what it should be when we're sort of done with this whole process there like that. So those are the 4 cases that make up erase there like that. Now, push back, pop front, push, all of those sort of 4 friends here, right? Those are all just one-liners that use insert and erase, and they all just run in constant time, in O of 1 time there like that. So if your insert and your erase are sort of coded correctly, they can handle all 4 of those situations, adding new nodes at the beginning, adding new nodes at the end, removing the head, removing the tail here. So all of these should just be like one-liners that just call insert and erase there like that. None of them require any sort of looping or anything like that. If you're expecting me to show you the code for insert and erase and the related doubly linked stuff here, you're going to be disappointed, because doubly linked lists are the topic of assignment 2. So you can check out the assignment 2 video, which will give you an overview of like what you sort of need to do as part of it there. But basically you're going to follow the diagrams and stuff in this one to implement insert and erase, and then a few other sort of related operations. Again, any of the operations that are just like, oh, start at the head and go forward, you can reuse the code from the singly linked list that we sort of saw earlier here. But anything that creates or removes nodes is going to need to be updated to be aware of those previous pointers there like that. If you write insert and erase first, I'll give you a sort of hint here, right? If you write insert and erase first, you can kind of like collapse the implementations, because there's a lot of overlap between the different cases. So you can kind of smoosh them down. It doesn't have to be like a big 4-way if else. And then if your insert and erase are implemented correctly, then push front, push back, pop back, those should all be just like one-liners that sort of rely on it there. So if you want to get started on assignment 2, pop over into the assignment 2 video and check that one out for some details on what that looks like.